In mathematics, especially order theory, a weak ordering is a mathematical formalization of the intuitive notion of a ranking of a set, some of whose members may be tied with each other. Weak orders are a generalization of totally ordered sets and are in turn generalized by partially ordered sets and preorders. There are several common ways of formalizing weak orderings, that are different from each other, but cryptomorphic. They may be axiomatized as strict weak orderings, as total preorders, or as ordered partitions. In many cases another representation called a preferential arrangement based on a utility function is also possible. Weak orderings are counted by the ordered Bell numbers. They are used in computer science as part of partition refinement algorithms, and in the C++ standard library. Examples: in horse racing, the use of photo finishes has eliminated some, but not all, ties or dead heats. So the outcome of a horse race may be modeled by a weak ordering. In an example from the Maryland Hunt Cup steeplechase in 2007, the Bruce was the clear winner. But two horses, Bug River and Leah Charm, tied for second place. With the remaining horses farther back, three horses did not finish. In the weak ordering describing this outcome, the Bruce would be first. Bug River and Leah Charm would be ranked after the Bruce but before all the other horses that finished. And the three horses that did not finish would be placed last in the order but tied with each other. The points of the Euclidean plane may be ordered by their distance from the origin. Giving another example of a weak ordering with infinitely many elements, infinitely many subsets of tied elements, and infinitely many points within these subsets. Although this ordering has a smallest element, it does not have any second smallest elements, nor any largest element. Opinion polling in political elections provides an example of a type of ordering that resembles weak orderings, but is better modeled mathematically in other ways. In the results of a poll, one candidate may be clearly ahead of another, or the two candidates may be statistically tied, meaning not that their poll results are equal but rather that they are within the margin of error of each other. However, if candidate X is statistically tied with Y, and Y is statistically tied with Z, it might still be possible for X to be clearly better than Z, so being tied is not in this case a transitive relation. Because of this possibility, rankings of this type are better modeled as semi-orders than as weak orderings. Axiomatizations. Strict weak orderings. A strict weak ordering is a binary relation less than on a set S that is a strict partial order in which the relation, neither A less than B, nor B less than A, is transitive. The equivalence classes of this incomparability relation partition the elements of S, and are totally ordered by less than. Conversely, any total order on a partition of S gives rise to a strict weak ordering in which X less than Y if and only if there exists sets A and B in the partition, with X in A, Y in B, and A less than B in the total order. As a non-example, consider the partial order in the set A, B, C, defined by the relationship B less than C. The pairs A, B and A, C are incomparable but B and C are related. So incomparability does not form an equivalence relation, and this example is not a strict weak ordering. A strict weak ordering has the following properties. For all X and Y in S, for all X, it is not the case that X less than X. For all X, Y, if X less than Y, then it is not the case that Y less than X. For all X, Y, and Z, if X less than Y and Y less than Z, then X less than Z. For all X, Y, and Z, if X is incomparable with Y, and Y is incomparable with Z, then X is incomparable with Z. This list of properties is somewhat redundant, as asymmetry follows readily from irreflexivity and transitivity. Transitivity of incomparability can also be stated in the following forms. If X less than Y, then for all Z, either X less than Z or Z less than Y or both. Or, if X is incomparable with Y, then for all ZX, ZY, either or. Total preorders. Strict weak orders are very closely related to total preorders or weak orders. And the same mathematical concepts that can be modeled with strict weak orderings can be modeled equally well with total preorders. A total preorder or weak order is a preorder that is total, that is, no pair of items is incomparable. A total preorder satisfies the following properties. For all x, y, and z, if x, y, and y, z, then x, z. For all x and y, x, y, or y, x. Hence, for all x, x, x. A total order is a total preorder which is antisymmetric, in other words, which is also a partial order. Total preorders are sometimes also called preference relations. The complement of a strict weak order is a total preorder, and vice versa. But it seems more natural to relate strict weak orders and total preorders in a way that preserves rather than reverses the order of the elements. Thus we take the inverse of the complement. For a strict weak ordering less than, define a total preorder by setting x, y whenever it is not the case that y less than x. In the other direction, to define a strict weak ordering less than from a total preorder, set x less than y whenever it is not the case that y x. In any preorder there is a corresponding equivalence relation where two elements x and y are defined as equivalent if x, y and y x. In the case of a total preorder, the corresponding partial order on the set of equivalence classes is a total order. Two elements are equivalent in a total preorder if and only if they are incomparable in the corresponding strict weak ordering. Ordered partitions. A partition of a set S is a family of disjoint subsets of S that have S as their union. A partition, together with a total order on the sets of the partition, gives a structure called by Richard P. Stanley an ordered partition and by Theodore Motzkin a list of sets. An ordered partition of a finite set may be written as a finite sequence of the sets in the partition. For instance, the three ordered partitions of the set A, B, are A, B, B, A, and A, B. In a strict weak ordering, the equivalence classes of incomparability give a set partition, in which the sets inherit a total ordering from their elements, giving rise to an ordered partition. In the other direction, any ordered partition gives rise to a strict weak ordering in which two elements are incomparable when they belong to the same set in the partition, and otherwise inherit the order of the sets that contain them. Representation by functions for sets of sufficiently small cardinality. A third axiomatization is possible, based on real-valued functions. If x is any set and f a real-valued function on x, then f induces a strict weak order on x by setting a less than b if and only if f less than f. The associated total preorder is given by setting ab if and only if ff, and the associated equivalence by setting ab if and only if f equals f. The relations do not change when f is replaced by g(f), where g is a strictly increasing real-valued function defined on at least the range of f. Thus, e.g., a utility function defines a preference relation. In this context, weak orderings are also known as preferential arrangements. If x is finite or countable, every weak order on x can be represented by a function in this way. However, there exist strict weak orders that have no corresponding real function. For example, there is no such function for the lexicographic order on Rn. Thus, while in most preference relation models the relation defines a utility function up to order-preserving transformations, there is no such function for lexicographic preferences. More generally, if x is a set, and y is a set with a strict weak ordering, less than, and f a function from x to y, then f induces a strict weak ordering on x by setting a less than b if and only if f less than f. As before, the associated total preorder is given by setting ab if and only if ff, and the associated equivalence by setting ab if and only if ff. It is not assumed here that f is an injective function, so a class of two equivalent elements on y may induce a larger class of equivalent elements on x. Also, f is not assumed to be an surjective function, so a class of equivalent elements on y may induce a smaller or empty class on x. However, the function f induces an injective function that maps the partition on X to that on Y. Thus, in the case of finite partitions, the number of classes in X is less than or equal to the number of classes on Y. Related types of ordering. Semi-orders generalize strict weak orderings, but do not assume transitivity of incomparability. A strict weak order that is trichotomous is called a strict total order. The total preorder, which is the inverse of its complement, is in this case a total order. For a strict weak order, less than, another associated reflexive relation is its reflexive closure, a partial order. The two associated reflexive relations differ with regard to different A and B, for which neither A less than B nor B less than A. In the total preorder corresponding to a strict weak order we get A, B and BA, while in the partial order given by the reflexive closure we get neither a B nor BA. For strict total orders, these two associated reflexive relations are the same. The corresponding total order, the reflexive closure of a strict weak ordering, is a type of series parallel partial order. All weak orders on a finite set. Combinatorial enumeration. The number of distinct weak orders on an n-element set is given by the following sequence. These numbers are also called the Fubini numbers or ordered Bell numbers. For example, for a set of 3 labeled items, there is one weak order in which all 3 items are tied. There are 3 ways of partitioning the items into one singleton set and one group of 2 tied items, and each of these partitions gives 2 weak orders, giving 6 weak orders of this type. And there is a single way of partitioning the set into 3 singletons, which can be totally ordered in 6 different ways. Thus, altogether, there are 13 different weak orders on 3 items. Adjacency structure. Unlike for partial orders, the family of weak orderings on a given finite set is not in general connected by moves that add or remove a single order relation to a given ordering. For instance, for 3 elements, the ordering in which all 3 elements are tied differs by at least 2 pairs from any other weak ordering on the same set. In either the strict weak ordering or total preorder axiomatizations, however, a different kind of move is possible, in which the weak orderings on a set are more highly connected. Define a dichotomy to be a weak ordering with 2 equivalence classes, and define a dichotomy to be compatible with a given weak ordering if every 2 elements that are related in the ordering are either related in the same way or tied in the dichotomy. Alternatively, a dichotomy may be defined as a Dedekind cut for a weak ordering. Then a weak ordering may be characterized by its set of compatible dichotomies. For a finite set of labeled items, every pair of weak orderings may be connected to each other by a sequence of moves that add or remove one dichotomy at a time to or from this set of dichotomies. Moreover, the undirected graph that has the weak orderings as its vertices, and these moves as its edges, forms a partial cube. Geometrically, the total orderings of a given finite set may be represented as the vertices of a permutohedron, and the dichotomies on this same set as the facets of the permutohedron. In this geometric representation, the weak orderings on the set correspond to the faces of all different dimensions of the permutohedron. The codimension of a face gives the number of equivalence classes in the corresponding weak ordering. In this geometric representation, the partial cube of moves on weak orderings is the graph describing the covering relation of the face lattice of the permutohedron. For instance, for n equals 3, the permutohedron on 3 elements is just a regular hexagon. The face lattice of the hexagon has 13 elements. 1 hexagon, 6 edges, and 6 vertices, corresponding to the 1 completely tied weak ordering, 6 weak orderings with 1 tie, and 6 total orderings. The graph of moves on these 13 weak orderings is shown in the figure. Applications. As mentioned above, weak orders have applications in utility theory, in linear programming and other types of combinatorial optimization problem. The prioritization of solutions or of bases is often given by a weak order, determined by a real-valued objective function. The phenomenon of ties in these orderings is called degeneracy, and several types of tie-breaking rule have been used to refine this weak ordering into a total ordering in order to prevent problems caused by degeneracy. Weak orders have also been used in computer science, in partition refinement-based algorithms for lexicographic breadth-first search and lexicographic topological ordering. In these algorithms, a weak ordering on the vertices of a graph is gradually refined over the course of the algorithm, eventually producing a total ordering that is the output of the algorithm. In the standard library for the C++ programming language, the set and multiset data types sort their input by a comparison function that is specified at the time of template instantiation, and that is assumed to implement a strict weak ordering.